Hello. We will introduce our recent work, titled CyberV, Cybernetics for Test Time Scaling in Video Understanding. This project aims to improve how multimodal large language models perform video understanding at inference time through a novel cybernetic framework. Current state-of-the-art MLLMs, including QWEN 2.5VL and Intern VL3, face several limitations when dealing with complex and abundant video content. These issues include limited token capacity, poor reasoning ability, and weak robustness. Fundamentally, this stems from their single-pass feed-forward architecture, which lacks mechanisms for adaptive control and self-correction. One way to address this problem is to perform test-time scaling to improve response accuracy. While test-time scaling techniques like chain-of-thought prompting or reflection-based strategies have shown promise in natural language processing, we find that they do not transfer well to video understanding. Simple chain-of-thought prompt and multi-round methods like wait even degrade performance instead of improving it, due to modality misalignment and reasoning drift. Furthermore, many existing video chain-of-thought prompting methods decompose complex reasoning tasks into manageable subproblems, addressing them step by step from low-level perception or auxiliary models. However, most of them rely heavily on supervised post-training or the use of auxiliary models. To address these challenges, our goal is to enhance video understanding at test time through adaptive control. We want the model to dynamically respond to different types of questions and content while monitoring and correcting its own outputs. For example, we expect the model to engage in reasoning for logic-oriented questions, while for perception-heavy questions, we prefer it to seek out more visual key cues. We propose incorporating principles from Cybernetics, the study of control, communication, and self-regulation in systems, into the design of MLLMs for video understanding. Cybernetics provides a rich theoretical framework centered on feedback loops, adaptive control, and goal-oriented behavior, enabling stable and effective operation in complex, dynamic settings. Inspired by principles of cybernetics, we introduce CyberV, a training-free and modular framework designed to build more robust and accurate MLLMs. Our experiments demonstrate that this method can remarkably improve the performance of a relatively small model by a large margin. It improves the accuracy of QWEN 2.5VL7B by 8.3% and Intern VL3 to 8B by 5.5%, allowing both models to surpass GPT-4o on the VideoMMMU benchmark. Furthermore, when applied to a larger model, QWEN 2.5VL72B, our approach yields a 10.0% improvement over the baseline, achieving performance comparable to human experts. CyberV views test-time video understanding as a closed-loop control process. It consists of three core components: the MLLM inference system. This is the plant in the cybernetic loop, responsible for executing inference over multimodal input. These responses serve as raw material for further evaluation. The sensor, which monitors the forward execution of the MLLM and extracts key signals such as predicted options and attention drift among different responses. These signals reflect the inference reliability, forming the basis for later decision-making. The controller is the central decision-making unit of the cybernetic system. It receives multiple signals from the sensor and evaluates the confidence of each candidate response using a rule-based scoring ensemble. Based on a thresholding policy, it decides whether to accept the output or trigger further inference with generated feedback. This slide shows the overall framework. CyberV begins with multi-strategy inference, then uses a sensor module to extract critical signals. The controller aggregates these signals and decides whether to accept the output or trigger inference feedback, such as attention-based keyframe augmentation. The revised input is then fed back into the MLLM, forming a closed-loop feedback cycle. Specifically, in the sensor module, we compare the attention maps of answer tokens across co-T-augmented and base model responses, focusing on the attention directed toward video and subtitle segments. By computing attention shifts, we identify frames where co-T reduces focus on the original visual content. Frames with the largest attention drop are interpreted as key regions requiring reattention and are selected as key frames. In the controller module, we propose a score forest that integrates multiple monitoring signals to compute a score for each candidate answer. If the score exceeds a predefined confidence threshold, the output is accepted. Otherwise, it is deemed unreliable and the self-correction mechanism is triggered. This mechanism can apply various forms of visual augmentation, including direct key frame injection, dense sampling of critical segments, or zoom-in enhancement. The controller then outputs an action that guides how the input should be revised for the next inference round. We evaluate CyberV on both knowledge-centric and general-purpose video benchmarks. VideoMMMU, 300 expert-level videos, ideal for evaluating symbolic and reasoning skills. VideoMME, 900 videos covering real-world domains like life, sports, and film. World Sense, over 1,600 videos spanning 26 diverse task types. Together, these benchmarks test a model's content understanding, reasoning, and generalization capabilities across varied video content. On VideoMMMU, CyberV consistently improves performance. It boosts QN 2.5 VL 7B by 3%, and intern VL 3 to 8B by 5.5%, both outperforming GPT-4o. When applied to QN 2.5 VL 72B, CyberV achieves a 10% gain, reaching performance on par with human experts. These results highlight CyberV's effectiveness in symbolic reasoning and logical deduction tasks. It excels particularly in comprehension and adaptation tracks, where reasoning and knowledge transfer are critical. Turning to general-purpose datasets, CyberV again shows consistent improvements. On VideoMME and World Sense, it achieves a plus 1.1% gain over the base model. Notably, these gains come despite the fact that co-T prompting alone actually degraded performance, emphasizing the value of our content-aware, feedback-driven control. In our ablation studies on VideoMMMU with QN 2.5 VL 7B, we observe that subtitles boost performance by 6.4%. Adding co-T further increases accuracy to 58.2%. Keyframe augmentation, which uses our simplest form of cybernetic loop, brings us to 60.0%. Furthermore, we compare BoN to tree search and find BoN offers a better trade-off between complexity and performance. Besides, subtitle-guided attention slightly enhances grounding, but may add noise if misaligned. We also evaluate the score forest against majority voting. Score forest achieves 63.3%, outperforming majority voting, 61.9%. We further test more visual feedback strategies. Dense temporal sampling yields 60.3%, while spatial zoom-in reaches 60.7%. Despite their efficacy, we default to simple key frame injection for efficiency. Moreover, to test robustness, we perturb the input by replacing uniform frame sampling with randomized offsets. CyberV maintains stable performance across all disturbance levels, consistently outperforming the baseline. This confirms the stability of our cybernetic control strategy under real-world noise. We visualize attention maps before and after co-T. The red boxes highlight segments where co-T reduced attention on critical content. By reintroducing these cues using keyframe feedback, CyberV corrects earlier mistakes, showcasing its self-correction ability. Here is an example that illustrates the model's successful identification of abnormal events in a complex video scene. Through iterative reasoning and re-examination, the model accurately detects an artillery attack, demonstrating the ability of the cybernetic loop to to refine attention and correct initial misinterpretations. In conclusion, we propose CyberV, a training-free framework for test-time scaling based on cybernetic feedback. By combining attention-based monitoring with adaptive control, CyberV enhances both small and large models, enabling them to outperform proprietary systems like GPT-4o. Looking ahead, we aim to explore more effective feedback signals, training-based improvements for temporal-grounded multimodal reasoning, and efficient control strategies. Thanks a lot for your watching.